for our objective today, we can't just call it tangents because we talked about tangents with regards to trig. So now our objective today is understand theorems relating to tangents of circles. So it's a different type of tangents that we're talking about. So this comes out of lesson 9-2. So remember, it's always a good idea to read your book to understand that. So we've got, let's see, 2 theorems, a corollary, and then a bunch of vocab that goes along with tangents. Ethan, Aiden, we're taking notes now. Okay, so let's start off with our first theorem, 9-1. First theorem of chapter 9. No name. And it states this. If a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. Okay. So if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So let's draw a picture of this and try to figure out why is it important to have a theorem like this. So we are going to be given that we have a line M is tangent to circle O at point T. Okay, so O refers to the center. M is the line that's tangent, T is the point of tangency. And we want to prove that segment OT or line OT is perpendicular to line M. So here's a picture. We've got our circle O, and we've got a tangent M. And according to this theorem, this point of tangency here, which is point T, if I drop a radius, and that's kind of, let me adjust his location a little bit. There's your point T. If I drop a radius from the center to the point of tangency, according to this theorem, it's now perpendicular. Those two would be perpendicular. So the radius is perpendicular to the line M. So OT is the radius, is perpendicular to the line M. And so how could you come up with this? How would this work? Well, we'd end up, this is going to come in handy when we're doing practices. It's going to help us with coming up with right angles, which could give us right triangles, which could give us 30, 60, 90, 45, 45, 90, depending on the situation. So that ability to create right angles is going to come in handy. We may end up using trig as well with this stuff, because anything that's a right triangle, we have a lot of different things to use with it. So there is my radius. And then you can see if you drew this value, oops, you can see that you can create that right triangle, okay? So that's the first one. Now, we've got a corollary that goes with this theorem 9-1. And the corollary states this. Tangents to a circle from a point are congruent. Okay. So let's illustrate this one. So I have a circle. Circle O. And let's say I have some point randomly out here. We'll call it P. And I'm going to draw more than one tangent to my circle. I'm going to label my 2 points here. This point of tangency would be point A. This point of tangency would be point B. According to this particular theorem, what it's saying is that the segment PA would be congruent to the segment PB. Okay, well, that's going to come in handy, because if I put that together with the first one and I drop a radius and then I connect up, I've got isosceles triangle, right? This guy here is going to be congruent to him. And I've got this big isosceles triangle. Therefore, when I drop that line down, I'm going to bisect that angle at the top. I'm going to be perpendicular bisector to the bottom. So yeah, there's all sorts of different things that can happen with this idea. Okay. Okay. So that's the corollary. And then we have another theorem. And it's theorem 9-2. And it says, if a line in the plane of a circle is perpendicular to the radius at its outer endpoint, then the line is tangent to the circle. Okay, wait a second. I have a line that's in the same plane of the circle. It's perpendicular to the radius at its outer endpoint. Then the line is tangent to the circle. What does that sound like? Yeah, sounds like the theorem 9-1's converse. That states you have a tangent, and it's going to be perpendicular to the radius that meets at the point of tangency. Well, that outer endpoint they're talking about would be considered the point of tangency. So basically, it's just the converse of theorem 9-1. So let's draw a picture of that one. So it's just a matter of the perspective of information. So we've got our circle, O, and we've got perpendicular, we have a radius. And this point here, I'm going to color him with something different. We'll call him R. And if we have a line that passes through R in such a way that it's perpendicular to the radius at that point R, we'll give it a name L. What we can say for our given is that L, let's do it this way, L is in the plane of circle O. We have to state that because that was in the hypothesis of our theorem. So they have to be in the same plane. They could not intersect if they weren't in the same plane. And then we were also told that line L is perpendicular to radius OR. And by the way, when you list the name of a radius, it's always center to circumference. Center to circumference. At point R, which by the way is the point of tangency, we would be able to conclude or prove that line L is tangent to our circle. Oh, okay, so that's basically what this theorem is telling us. Okay, so that's going to be helpful in doing some calculations down the line as well. All right, so that kind of concludes the theorem part. And remember, your whole point to homework is to apply these theorems in different ways. Now let's get some vocabulary under our belt. So remember what I said, that we're talking about a brand new shape. So anytime we talk about a brand new shape, in particular in geometry class, we have a ton of vocab words. So this is I think, what did I say, 26 vocab words? And the last chapter was 9. Because we were just same stuff over and over and over again. Now we're into new things. So let's talk about a common tangent. So again, anytime I'm using tangent in this chapter, I'm talking to a circle. So it's a line that is tangent to each of two coplanar circles. So there's that idea again, coplanar meaning they have to be in the same plane. Okay. So common tangent is a line that is tangent to each of two coplanar circles. So we're going to do a diagram, and from that diagram we're going to specify the types of tangents that you might see. All right, so let's, got a little circle here. We'll call them circle, I don't care, A. And we've got a bigger circle here. We'll call them circle B. I'm going to draw a line that would connect the two centers together. Okay. And then I'm going to draw two different tangents, and then we're going to discuss them. Okay. So what's crucial is how these tangents relate to that dashed line that connects the two centers. Let's see, this is going to be a little bit challenging for me. Yep, try that again. There we go. So we're going to call this point A up here, and we're going to call this point B. Oh, let's change letters. I already used those letters. Let's call this point C and point D. Okay. And then let's do a different one. So we'll call this E, and we'll call this F. Oops, hello, F. Okay. Now, we have two different tangents. One's called internal, and one's called external. What do you think, which one would be the internal one, the CD or the EF? CD, okay, good, yeah. So an internal tangent it's a tangent that joins, or that intersects, sorry, a segment joining the centers. So that would be line CD. He's the internal tangent. He's intersecting that line that would connect the two centers of that circle. That makes EF an external tangent. And how we would describe that is it's a tangent. This is going to be really a stretch here, okay? Are you guys ready for this? This is going to be tough. A tangent that does not intersect the segment joining, oops, these centers. How do you like that for a definition? Okay. A tangent, this is for Drake Plotkin, a tangent that does not intersect the segment joining the centers. Okay? All right, here comes some more definitions and some pictures to go with them. Everybody ready? All right, here we go. We need to talk about tangent circles. And circles can be tangent in a couple different ways. So another vocab word. Tangent circles are coplanar. Can't have much if they aren't in the same plane. Coplanar circles that are tangent to the same line at the same point. So if you think about it, circles are considered tangent circles if they have the same point of tangency. Okay? So they have, each of them have a tangent, they have a point of tangency, and they touch only the circles at that point of tangency. Okay? So there's two different types of tangent circles that you can have. Okay? And they relate back to the two types of tangents that you can have related to a circle in a sense. Okay? So we had internal tangents, we had external tangents. So we can have circles that are internally tangent and circles that are externally tangent. All right? So let's start with internal. Okay. We have two circles, A and B. We have a line that's tangent. These two circles have exactly one point in common. It's that point right there. That is called the point of tangency. There's the one place where the two circles are tangent to each other because of the common tangent. So we would say these are internally tangent circles. They, one circle inside the other with a common point of tangency. And if we want, we could put a little letter there. We'll call that C. Okay. Yes, that's why it's underlined. So what do you think the externally tangent circles would look like? Dakota? Yeah. We've got not one inside of the other, one butting up to each other. But exactly how many points do they have in common? Only one. So let's see if I can draw that picture. We'll call him circle B. Oops. We'll call him, oops. There we go. A little harder. Circle A. They have exactly one point in common. That's point C. And it's only through that one point does the tangent pass. Okay? What's really hard for us is that because our lines are so thick and because of the inaccuracies of human drawings, it looks like they have multiple points from the circumference in common, but they don't. It's literally just one point that touches the other circle. Okay, so that's the part you have to kind of suspend what you're seeing and trust what you're being told. Drake.
The line AD is perpendicular to the line, or the tangent line, right?
AC, if I drew this correctly, it would be AC would be perpendicular to the tangent that C is part of, and then BC would be perpendicular to that as well. So then they would be, should be one continuous line, okay? So these are external, oh, I forgot a word here, didn't I? Externally tangent circles. And this, that was internally tangent, and then these would be externally tangent circles. You have two circles, let's see, I guess we could say adjacent. Adjacent with only one common point of tangency. So the difference between internally is one circle's inside the other with that point, common point of tangency. Externally, they're adjacent or outside of each other, okay, with only one point of common point of tangency. All right, that's it for the notes.